Okay, so in the last series of videos, we started developing the machinery for non-inertial reference systems. And I did say that one of the trite reasons why we were interested in this is because the surface of the Earth is a non-inertial frame, and so it'd be helpful to know how to adjust for that. So with that, we will go ahead and take a look at the effects of the Earth's rotation in this video. And then in the next video, we will look at the very specific example of the Foucault pendulum, because it is very instructive. Okay, so first off, let's just go and take a look at the static effects. I mean, granted, the Earth's surface is rotating, but we're pretending it's not, so that's why we can call it static. So we'll start by drawing us a good-sized Earth, like so. And we will go ahead and put in a inertial coordinate system centered on the Earth like so. X, Y, Z. But that's not where we actually do our observations from, right? We instead will do our observations from some point on the surface of the Earth. And of course, this point on the surface of the Earth is rotating, but there's our proposed coordinate system for the moment. X, Y, Z, like that. Now, let's dimension this out while we're at it. This angle here corresponds to our latitude. And I'll mark off the position vector of our coordinate system R at our observation location. Now, near the surface of the Earth, we'd like to actually think that G, the gravitational field vector, would actually point in the direction the pendulum bob hangs. Well, if we think about that carefully, we realize that that's going to mean it's not going to hang quite to the center of the Earth, except at a couple of special locations on the surface of the Earth. But instead it's going to deflect off a little bit. Let's go ahead and take a look at that. So what we'll do is we'll go ahead and draw a free body diagram in our accelerated frame here. So here angled at our latitude, I'll call that mg naught, where this is referring to the pure gravitational field part of it. But if we think about this here, we're rotating around in a circle like so. So that means that we're going to be feeling a centrifugal force pushing us out. Now this is greatly exaggerated compared to the force of gravity. In fact, let me make the vector shorter, and even so, this is greatly exaggerated. This will be our minus m omega cross omega cross r. Okay. So with that, we can go ahead and write our Newton's second law for our pendulum bob, and we're going to do that in the rotating frame. So our force is mg naught. Since this is a pendulum bob, we've also got a force of tension acting. So let me draw that in too. So plus a force of tension minus m a naught minus 2m omega cross v prime minus m omega dot cross r prime minus m omega cross r prime, and all of that is going to equal m a prime. Okay, now the transverse force term here, we can make that go away. And this is because, yes, the Earth's rotation rate is slowing down, but it's not enough to write home about. I mean, geez, we can take care of that by adding an extra second to the year about every 5, 6 years, decade, something like that. So for our purposes, we can ruthlessly ignore the fact that the Earth is slowing down in its rotation. Okay, on the other hand, finding this a naught, that's going to be a bigger deal. So let's go ahead and start doing that. So we'll find our a naught. All right. So again, here's an Earth. So our coordinates, our primed coordinate system is located r naught out. And then we're going to be observing at some point nearby, but I'm going to have to greatly exaggerate this just to make the drawing plausible. So there's our prime, like so, and then this would be our r. Okay, so our a naught will equal d squared r naught dt squared in the fixed frame. So we're going to have to take the time derivative in the fixed frame twice. Fixed, fixed, like that. All right, and so remember what the prescription is for each of those. So we'll do the inner one first, so d dt of. So to take the time derivative of this, we can take the time derivative of it in the rotating frame, dr naught dt in the rotating frame. Thankfully, that's 0. Plus, we pick up an omega cross r naught. And then we will have to evaluate the derivative of the omega cross r naught in the fixed frame. So we do the same process again. So my a naught is going to become, keep in mind our a naught is pointing in, straight into the center of rotation for the circle you're going around at your latitude. So we do it again. We go ahead and take the time derivative of this cross product in the rotating frame and then add a omega naught cross that. Okay, so this will become d omega dt in the rotating frame crossed with r naught. We've already said we're going, over a period of time of anything we care about, we're going to ruthlessly ignore the fact that the Earth's rotation is slowing, plus omega cross dr naught dt as measured in the rotating frame. And again, we can ruthlessly make that go to 0 because that's the whole point of working the rotating frame, is that we don't think we're moving. So that just leaves us with plus omega cross r naught. Okay, so now that we've got our a naught term worked out, we can revisit our Newton's second law. So now we've got an mg naught like before, plus our tension. Now we can say minus m a naught, so this will be minus m times omega cross r naught We've already wished away the transverse force because we said that omega dot is 0 for our purposes. We still have the Coriolis force, so minus 2m omega cross v prime minus the centrifugal force m omega cross little r prime, like so, and that equals m a prime. All right, so we can clean this up just a little bit. So we'll have the force as measured in the rotating frame will be the tension plus, if we group stuff around a bit, we'll have an m times g naught minus omega cross r prime plus r naught minus 2m omega cross v prime, and that will equal our m a prime. Okay, now since we're looking at a static bob here, we're not letting it swing yet. For a static bob, v prime is 0. So that will give me that my apparent force, or my observed force, mg, will equal m times our g naught minus omega cross r prime plus r naught. And we can cancel the m's. Now, let's face it. If we're going to be looking at, say, something like a pendulum swinging, we're not going to be, compared to how far away we are from the center of the Earth, this r prime is basically negligible. It won't shift our, relative to the Earth, it's not going to shift our location too far off of where we're currently standing on the surface. Basically, if you can breathe air, or heck, if you're even just worried about air, you're within 100 kilometers of the surface of the Earth. The radius of the Earth is a lot bigger than that, so it's just not worth really writing home about. So we finally get that our observed g is equal to the actual gravitational field vector minus omega cross r naught. Alrighty then. So let's try to get some feel for how big that is and how far that would deflect our pendulum bob. So going back to the Earth here, we're going to rotate at omega, like so. We are located here, say at this point right here on the surface of the Earth. There's our r naught, and that is located at our latitude. Okie dokie. So if we go ahead and draw in a free body diagram for our pendulum bob, we have our mg naught, and this is greatly exaggerated here. This is our minus m omega cross r naught bit right there. Takes me, and then that will give me my resultant observed mg, like so. Okay, so now this angle here is the latitude, and we'll just call this angle here epsilon to get some idea of the deflection of our the g we observe due to the on the surface of the Earth due to the g that's due purely to gravitational effect. All right, so we can do that. We can start with that. Let's just go ahead and evaluate the magnitude of our sideways deflection. So this is, we want to find the magnitude of omega cross r naught. Well, alrighty. The easy bit is going to be the magnitude of omega crossed into whatever this is. The cross product is guaranteed to be at right angles to the things that make it up. So we're omega cross something that's guaranteed to be perpendicular will give us a sine of 90, which is 1. So it'll be equal to omega times the magnitude of the cross product inside. Well, that will be omega times r naught times the sine of the angle between them if I were to go and put them together tail to tail. So that's going to be the sine of 90 degrees minus lambda. But that's the same difference as the cosine, so we can write that as omega squared r naught times the cosine of the latitude. All right, so now with that we can look back at this triangle here, and we can do the law of sines. We can say that the sine of epsilon is to the length of the leg across it, which we just figured out was m omega squared r naught cos lambda, as, now looking at this angle here, the sine of lambda is to the angle to the leg across it, which is just plain mg. Okay, we can cancel the m's. That's cool. So what we get is that the sine, the sine of our epsilon is, which is hey, this angle is going to be small, so you can just call it epsilon directly, will be equal to omega squared r naught over g times the sine of lambda cosine of lambda, and we remember that that is 1/2 of the sine of 2 lambda if we looked it up in our trig tables like I had to. And so we get that our deflection angle in radians is approximately, and it's a really good approximation, omega squared r naught over 2g times the sine of twice your latitude. All right. Now this deflection will max out by inspection at 45 degrees. So northern lower Michigan has the worst deflection on the planet. So think of that the next time you drive up to the UP and you cross that 45th parallel sign. So it maxes out at 45 degrees, and if you crunch the numbers, our maximum epsilon is on the order of about 1/10 of a degree. So it's not huge. It's not really, in most of the rest of the Earth, the deflection is going to be even smaller than that. It's the sort of thing that keeps surveyors up at night, but for the rest of us, not a big deal. But if you're a geologist, it is a kind of big deal, because the Earth's surface is plastic. So instead of the Earth really being this perfect sphere we were talking about, the surface of the Earth is going to move around to always be perpendicular to where the local gravitational field vector is. So that means like here and here, we would expect it at right angles to the surface. Well, I expect it at right angles to the surface everywhere. Let's say here at 45 degrees. Now here I'm greatly exaggerating our G there, and I am greatly exaggerating it. It points off center. So the correct surface that we need is one that will cross perpendicular everywhere, like that. Oh, geez, can I do a better job drawing it? No. The hard part to believe is that my mom made her living as an artist. Shows how far the nut can fall from the tree sometimes. All right, so anyways, everywhere I'm attempting to draw an oblate spheroid. And you know this is an oblate spheroid because I labeled it as such. So basically, the Earth has packed a few extra gravity snacks around its equator. This also has a slight effect. This means that G at the equator, because of the shell theorem, we can have a little bigger shell here, the encompassing more of the mass of the Earth. G is going to be a little bigger here. That is at the poles where we exclude a little bit of the Earth that's outside the shell that intersects that point there. So we get that G at the equator is very slightly bigger than G at the poles. And this is slight. But it's why you never really see G quoted to more than 2 decimal places in most texts, and it is because of that slight variation. Okay, so with that as prologue, we've taken a look at the static case. Now let's go ahead and look at projectile motion. All right, now here we're going to want to make a different choice of coordinate system, of non-inertial system, just to better match our own reality, our own experiences anyway. So there's omega. Again, the Earth rotates like that. And we are here. So that angle there, again, is our latitude. Okay, now our choice of coordinate system that we'll want is we want our K prime so our z-axis, we want it to point such that G is equal to minus G times K prime. So perpendicular to the surface of the Earth. And since we worked out that even the worst case scenario in northern lower Michigan, the deflection is off by most 1/10 of a degree. You know, unless we're getting super careful, we can pretty much just say that that's pointing straight into the center of the Earth, so don't get too strung out about it. But if you want to throw in the plus and minus epsilons, go right ahead. Anyway, we will want our y-axis here to point north, like so. So there's my j hat. And then my I hat points into the page, so that is pointing east. So this is, so what we've tried to set up is in local terms, I hat is east, j hat is north, and k prime points what we locally think of as up. Like I say, if you want to throw in the plus and minus epsilons, be my guess, but it's not going to change anything very much. So, if we look at this, this does mean that our omega, when we put it into the primed coordinate system, we're going to have the x prime component of omega is 0. But for the y component, omega y prime, that will be equal to omega times, here let's just draw it over here to think about it a little better, omega k prime points that way, j prime points that way, this angle is lambda, sorry, my bad, this angle here is lambda, this angle here is 90 degrees minus lambda. So this will be omega cosine lambda, and then for the z prime, that will be omega sine lambda, and you should convince yourself of that. All right, so if we go back to our Newton's second law in rotating frame and recast it for our projectile motion case, we're going to have the physical forces F plus actual gravity, so this is external to gravity, minus our ma naught, and we're going to roll all of that into our local mg. Then we'll have the Coriolis force 2m omega cross v prime, and our centrifugal force trying to throw us off the surface of the Earth, m omega cross r prime. And that will equal our m a prime. Now, we're going to make this go to, just so we can get something that's tractable. Let's, for now anyway, neglect air resistance. And we can kind of wish the centrifugal force term away as well. And there's a couple of reasons for that. First off, the Coriolis force term is of order omega. This is of order omega squared. Now, what is omega here on the surface of the Earth? Think about that for a moment. I'll pause and give you the answer. It's 2 pi over 24 hours. So once you get your hours into seconds, it ain't much. And so then when we square it, it's really small. Also, the A naught, remember, sure, it has an omega cross r in there, but that's r naught. That's the distance from the center of the Earth to our point of interest. And the magnitude of that r prime is way small compared to that. So because of the omega squared, it's really small compared to the Coriolis force. And because the r prime is so small compared to the radius of the Earth, that makes it small compared to the local mg. So either way we go, it's small. All right, so we can then go ahead and cancel our m's because we made the air resistance go away. And so we are left with r double dot in the prime system equals g minus the Coriolis acceleration, omega cross r dot. I'll give that a name. Okay, So first step here is let's just go ahead and find our omega cross our dot. We'll just do that by good old-fashioned take the cross product. So I, J, K with primes, omega x prime, omega y prime. Oops, there we go. Omega z prime, x dot prime, y prime dot, z prime dot. Okay. And remember, we said omega x prime was 0 because there's no component of the rotation vector in the eastward direction. Okay. So that'll make the cross product taking go a little easier. So our omega cross our dot equals, well, let's first go find the I component. So that will be I times omega y prime z prime z prime dot minus, plow the field the other way, omega z prime y prime dot. And let's see, in the j direction, so plus j prime. Okay, we go this way. We're going to get an omega z z prime x dot. And then the other direction, we get 0 going through the omega x part right there. Then finally, for the k, plus k prime, we plow the field this way, we get nothing. We plow the field that way, we'll get a minus. So actually that plus should become a minus. K prime times omega y prime x prime dot. Okay, so if we got that, we'll take this, we will plug that back into double star there, and we will equate our components. So when you do that, you will get x double dot prime equals minus 2 omega z dot prime cosine lambda minus y dot prime sine lambda. Y double dot equals minus 2 omega x prime dot sine lambda, and z prime double dot equals minus g plus 2 omega x dot cos lambda. Just so we can keep track of these, I'm going to call this 1, 2, and 3 like that. Now, you can't separate these, so it's not worth trying, but you can integrate them. And as you can guess, we're going to start doing some successive approximations to try to get something more tractable. So we'll integrate these once. That'll give me an x dot prime equals minus 2 omega z prime cos lambda minus y prime sine lambda. That's why I love the dot notation. You integrate something, you can just kiss the dot bye-bye. Plus, we have to add in the initial condition. Similarly, y prime dot will be minus 2 omega x prime sine lambda plus the initial condition. And z prime is going to be minus gt plus 2 omega, whoops, that should be a prime there, 2 omega x prime cosine lambda plus z naught dot prime. All right, and we'll call that set 4, 5, and 6. Now, this will allow us to at least approximately separate equations 1 through 3, which is what we're trying to solve. The trick is you can take equations 5 and 6 and plug them into equation 1. By doing that, you can then get a second order differential equation in terms of x alone. So at least that is something that we can cope with. All right, so we go ahead and do that. We'll have, so this becomes x double dot prime is equal to 2 omega gt cos lambda minus 2 omega times 2 omega x prime cos lambda plus 2 omega times minus 2 omega x prime sine lambda minus 2 omega z naught dot prime cos lambda plus 2 omega y naught dot prime sine lambda. All right, that looks heinous, but again, don't freak out. Reason is that this term is approximately 0, and so is that one. Because again, remember, omega is small for the rotation of the Earth. So these goes omega squared. So again, we're making them go away. All right, so we can clean that mess up a little bit. And we get x prime, which we'll need that anyway, is going to be, oops, sorry, don't want to integrate just yet. My bad. X double dot, just cleaned up here, is going to be 2 omega gt cos lambda. And we can do a little bit of grouping. Minus 2 omega times z naught dot prime cos lambda minus y naught dot prime sine lambda. All right, now we can go ahead and take that puppy and integrate it twice. So first time x prime is going to be, well, squared, bring down a half, cancels that 2. So you're going to get omega gt squared cos lambda. And then you're going to, this stuff is all constant. Excuse me. This stuff is all constant, so you're going to pick up what you had before. So minus 2 omega t times that stuff in the parentheses. Plus we have an integration constant, so we'll pick up a plus x naught dot prime like that. Oh, let's make that look a little better. There, much better. All right, and then to get our x, we need to integrate this one more time. So this will give me x prime is equal to, integrating that will give me 1/3 omega gt cubed cos lambda. Integrating this will give me 1/2 t squared, but I got 2. So this will be minus omega t squared times z naught dot prime cos lambda minus y naught dot prime sine lambda plus x naught dot prime t plus x naught prime. All right, so we have our x as a function of time. All right, now to get the y, let's go ahead and call this guy here equation 7. So what we're going to do is we're going to take that and we're going to stick that in where we have our x prime, we're going to stick that in to our equation 5. So equation 7 goes into equation 5. When you do, you get y prime dot is minus 2 omega sine lambda times 1/3 omega gt cubed cos lambda minus omega t squared times the stuff in the parentheses from up there that I don't really feel like writing again because we're going to make it go away in just a moment, plus x naught dot prime t plus x naught prime plus our initial condition y naught dot prime. And these two terms here, this guy and this guy, are both approximately 0. And again, it's the same deal. Omega times omega, it's going as omega squared. It's very small compared to these terms that are going as omega. Ditto this guy here, which is why I didn't bother writing that stuff in. Okay, so since I made that stuff go away, when we integrate one more time to get our y prime, we have minus omega x naught dot prime t squared sine lambda minus 2 omega x naught prime t sine lambda plus y naught dot prime t plus y naught. Oops. Plus, don't do that to me. There, why not? All right, we'll call that guy equation 8, just for keeping score. By the way, if you are following with your text, this term here was dropped by your text. No particular reason why not to keep it other than once the time grows substantially, probably this term's going to dominate versus that guy. But I don't see any particular reason to drop it, at least not yet. All right. So then similarly to solve our equation, solve for z, we can again take our solution from equation 7, and now we can stick that into equation 6 and see what we get. So equation 7 going into equation 6. So that's going to give me a z prime equals minus gt plus 2 omega cos lambda times 1/2 omega gt cubed cos lambda minus omega t squared times that stuff in the parentheses that again I'm not going to care about because I'm going to make it go away, plus x naught dot prime t plus x naught prime plus our initial condition z naught dot prime. Alrighty. So as before, this term we're going to make approximately 0. And that term we're going to make approximately 0 because, again, they're of order omega squared, and omega is already small. So integrating, what's left, we'll have z, we will have z prime equals minus 1/2 gt squared. Yay, some things still behave the way we like them to. Plus, we'll have a omega x naught dot prime t squared cos lambda plus a term that your text dropped, and again I don't see a burning reason to drop it, plus 2 omega x naught prime t cos lambda plus z naught dot prime t plus z naught prime. Phew. And that's our answer for z. And for keeping score at home, we'll call that equation 9. All right. That was a lot of work, so we should probably go back to something comfortable, like let's drop a rock. So this is, we're revisiting example 541 in your text. So I'm dropping a rock from rest, some height h, like so, and it's going to land sideways at some location x prime as a function of time. So it's going to go like that is our trajectory. Since we're dropping from rest, we can say, and we can choose our coordinate down here, probably makes the most sense. So our initial x naught prime and y naught prime are both 0. Z naught prime is h. We're dropping from rest, so we can say x naught dot prime equals y naught dot prime equals z naught dot prime equals 0. So with that, our equations 7 through 9 become x prime equals 1/3 omega gt cubed cos lambda, y prime equals 0, and z prime equals minus 1/2 gt squared plus h, which that at least looks comfortingly familiar. So to find the drift, we're going to go ahead and set z prime equal to 0, so they'll equal minus 1/2 gt squared plus h, and that will give us t is equal to the square root of 2h over g. All right, so then we can stick that into our x, and we get that x prime will equal 1/3 omega g times 2h over g to the 3/2 power times the cosine of lambda. If you want to clean that, make that look a little pretty, so we can at least get a square root symbol in there, we can at least bring the cube in. And here, when we bring this in, we bring the cube in, we'll have a g cubed in the basement, we got a g on top. So we end up with 1/3 omega 8h cubed. Whoops, let's do it this way. 1/3 omega times the square root of 8h cubed over g cosine lambda. So if we look at this, our result is positive. So this means that the drift is eastward. So if you were trying to explain this to an introductory physics student, the Earth churns west to east. So why does it make sense then that our rock would actually end up further east? Explaining this as you would to a 100 or 200 level student. So again, pause the video and I'll get back with you. Okay, the reason here is because if you think about it, you're further away from the surface of the Earth. So that means, from the perspective of an inertial frame, that the tangential velocity of the rock is a little greater than the tangential velocity of the surface of the Earth. So what that means is that as the rock drops, as the Earth is turning out from underneath it, it isn't doing it quite as it isn't turning quite as fast, and so that means the rock is doing a better job of moving east than the Earth is, and the rock ends up landing to the east. Okay, in the next video, we will tackle one of my all-time favorite systems, the Foucault pendulum.